The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, folks. I may not look like Don Sadoway, but for today, I am Don Sadoway. So let's, whoa, that's, boy, I guess you can hear me pretty well, right? Okay, Professor Sadoway is in a faraway, terrible place. It's called Vienna. Yeah, I know. We're here. What can I say? And he'll be back next Tuesday. And so my name is Ron Ballinger, and I'm taking his place. Oh, whoa. Put a muffler on that. Okay, great. I'm sure you're all anxious before we get started to see that. Right. The average, it was about 66, which is about 10 points lower than the last 5 or 10 quiz ones. So it's a little bit lower. It was a little bit harder test. I'm sure Professor Sadoway will mention this when he comes back, but for those of you who are below the 50 mark, it's time to do something about it. And when I mean do something about it, I'm sure your recitation instructors will be very happy to help out in any way possible, but there are other options, not the least of which is a tutor. And so if you think you need one, and you need to be kind of ruthless about examining yourself. If you think you need one, go down and see Hillary, and there are tutors which are available for individual instruction. So I think it's a great time to take advantage of that, because I can guarantee you that test number 2 will not be any easier. In fact, it'll be considerably harder, because it'll be pretty much new material. So, okay, so that's enough for that. Last day, I wasn't here. I was in Washington. They're actually trying to build what's called an Exaflop computer. Did anybody know what exa means? 10 to the 18th. 10 to the 18th floating point operations per second. Why do they need that? Because when you go beyond 3091 and start modeling these atoms, especially F-block atoms, you need a supercomputer that large. And to do one run on a petaflop machine takes 100,000 CPUs, 10 hours for one atom. So solving the Schrodinger equation is a bit tricky. Okay, remember last time we talked about metallic bonding, and we're sort of sneaking up on it. Remember Paul Drude. Well, let's look up here. These are the characteristics of metallic solids. They have high electrical conductivity. They have high thermal conductivity. They shine. And they have ductility. So we're going to deal with the first 3 today, and later on in the course we'll talk about the ductility part. But recall that Paul Drude modeled the solid as a series of cations, which amounted to the nucleus plus, get these outnumbered, I'm in trouble. A nucleus plus the inner core electrons, and then allowed the electrons, the outer shell electrons, the valence electrons, to float around, called it a free electron gas. And that model explained the temperature dependence of heat capacity, but it was not so good when it came to electrical conductivity. It explained the fact that you get electrical conductivity, but not the fact that some materials are conductors and some materials are insulators. So we need to deal with that. And for that, we need to talk to 2 sets of folks. The first one is Felix Bloch. All right? And he was 1928. he got his PhD under Heisenberg. These guys, boy, it would have been nice to be back in those days, working for those great folks. And he applied quantum mechanics to solids. Quantum mechanics to solids. And he said, okay, let's consider that in a solid, the atoms are arranged in an array. What's an array? Well, it's actually called a crystal. A crystal, all right? It's an ordered array of atoms, and we're going to say a lot more about that as we go along. And then he said, well, then let's apply the Schrodinger equation to this system. Now, it's a big difference between the Schrodinger equation for a single atom in a gas and multiple atoms in a solid. It's a different set of boundary conditions, different set of conditions altogether. And when you do that, you get a set of solutions for the valence electrons which is, as you might expect, it's periodic. It's periodic, and it invokes wave-like properties of the electron. So, and you end up with a set of values of the wavelengths for the electron that are such that it allows mobility, which is, after all, what we're after. These electrons got to move through the solid if we're going to have conductivity. All right, and this is an example where classical physics wouldn't allow that. All right, so you can't get this kind of the kind of behavior in with classical physics. So that's one piece. And the second group, two guys, Walter Heitler and Fritz London. We know Fritz London from London Dispersion Force, the same guy. These guys were very, very productive. And he did a postdoc. That's another word for slave labor, by the way. Folks will know that here. For guess who? Well, he did it for Schrodinger. Interesting story, I guess, that these guys showed up for their slave labor at Schrodinger's lab, only to discover that Schrodinger had taken a position at a different university. So these guys showed up, and he said goodbye. Anyway, that's a bummer, all right? Okay, and they sat down and they said, well, okay, let's see if we can go at this from an energy point of view, as opposed from the quantum mechanical point of view. And let's see if we can apply LCAOMO. Now, don't break out in hives because of the test. To a solid, all right? To large aggregates, large what? Of atoms. How big is large? Well, I don't know. Dream up a number. Say 10 to the 23rd. Lots of atoms, all right? And let's see what happens. Well, we've already done a little of this in the past. We looked at the energetics of the stability of hydrogen or the stability of helium, so we can take that and we can kind of add up, and we'll see what happens. Well, remember if we had atom A, and now let's only deal with the valence electrons, and so this would be 0, and there's another atom A, 0, and this would be A2. And we've been through this before. Let's just we know that we get splitting, and we get a sigma bonding orbital and a sigma star antibonding orbital. Well, let's start adding some atoms here, additional atoms. What do we get? Well, let's just forget A sub n, lots of atoms. Well, what do we get? We end up with what we end up with is, of course, up here is 0. We end up with lots of states. Remember, we have to have conservation of states. So for every atom we add, let's say this is copper, for example, right? Which has an S1, 1s. It's an odd number of electrons. So every time I add a copper to this, I add extra states. And then what do? I start filling them using Aufbau, just like we've done in the past. Well, if we keep going, and by the way, not to scale, it starts looking like a whole bunch of states. And this energy level here, these energies, what? We know for hydrogen, this is what? Minus 13.6 electron volts. So what are we dealing with here in terms of state differences, right? Well, let's take 10 to the 23rd atoms, and let's see if we can calculate an energy. Well, let's take for copper, the molar volume of copper is what? 7.11 centimeter cube per mole. All right, and that's 10 to the 23rd, well, actually 6.02 times 10 to the 23rd atoms. And let's just ask ourselves, what's the sort of range here? Well, we know that it's 13.6 here. We know that's 0. We're all friends. So let's call it 10 eV, just for grins, right? Not a bad number. And let's ask ourselves, well, if we've got 10 to the 23rd atoms and 10 eV, let's take 10 eV over 10 to the 23rd, and you get what? Well, 10 to the minus 22 eV per state. All right? 10 to the minus 23rd eV per state. That's small. That's really, 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 really small. And if you convert that to joules, you end up with 10 to the minus 41 joules. That's really small. That's really small. So what are we saying? We're saying that this organization here, when we add a lot of atoms, we put a lot of atoms in there, we end up with what amounts to a band. A band of states. A band of states. And what do? All right? We populate this band just like we did with using the Aufbau principle. But what does it really look like? Well, in the case of copper, right? Remember, copper has a 1s. 1s electron is 3d10 more. Copper is 3d10 s1. All right. So, excuse me. If we start filling this band, we're going to get. And so we start filling, spin pairing. And we get up here, and we find that we end up with a half-filled band. Because there are states that are not occupied. right? States that are not occupied. But remember, the distance between this guy and this guy, the unoccupied and an unoccupied state, is only 10 to the minus 41 joules. So that's pretty small. 10 to the minus 22 electron volts. To give you an example, 0.025 electron volts, which is, if you want to convert that to temperature, that's about 300 degrees Kelvin. So very, very small energy. So that means if I were to take if I were to apply a potential here, then what happens? Well, I add a little energy, and I don't have to add much energy, and it's very easy for me to promote more than one or more of these electrons up into the above here, and then I can get migration. So the end point is that if we apply a potential, we end up with conductivity, which is what we were after. Moreover, we can say a few more things. All right, these, if I shine. Now, this is a sort of mixed metaphor here. This is an energy diagram, and this is some plates on an electrode, so be a little bit careful. We shine photons on this thing. What happens? What's the energy of the photons of light? Between 200 or 400 and 700 nanometers. All right, it's about 1 electron volt. So there's plenty of electron volts here. I'm going to, with a metal, not only will I have conductivity, but there'll be enough energy here to promote electrons. And those electrons will move around, and we'll end up with re-emission, and we end up with opaqueness. In other words, we absorb light and re-emit it, and so we end up with, in the case of a metal, luster. All right? So those are a couple of things. So if we recall back here, we're talking about high electrical conductivity. We need to say a lot more about that, but we're okay here. But Drude was okay as well. High thermal conductivity, Drude did that. That was fine. Luster. Okay. So it works for copper. Seems to be okay. But what about another one, like, say, beryllium? All right? What's with beryllium? Well, beryllium is 2s2. Right? So now let's draw the thing for beryllium. We have beryllium, let's be 2s, and now let's 2p, all right? And we populate this. And now we want to add n beryllium atoms, all right? What's happening? Well, we got this band that we've talked about earlier. Now we go to fill it. All right, so we're filling these guys. And we fill it, and lo and behold, we find out that we fill it all the way to the top. And so we're screwed, right? We say, we have no conductivity, all right? Now, who else is on? What I can imagine now is there's 100 computers in here. 50 of them have Skype. Guess what's going to happen? By the time the end of the day is, there'll be 50 things up there. All right, so we know beryllium's a metal, all right? And it has conductivity. So what's the deal? Well, it turns out that while beryllium has 2s band full, the 2p orbitals still are there, right? And they're still there, and so there's going to be a band, all right? There's going to be a band unfilled. There's going to be a band for the 2p orbitals. Well, guess what? It turns out that the way I've drawn it, the 2p band overlaps the 2s band. And so what that means is that I can promote into the 2p band, and I can achieve my conductivity. So that's another. So we've solved the problem of the filled s orbitals. And we've got conductivity in both cases. All right, so we're okay. We're okay so far, but Drude wasn't far behind. Whoops. All right. This one's not working. Oh, yeah, it is. Okay. What can we say about insulators, right? It looks like we got a problem, all right? It looks like we have a problem. Well, let's take a look at another example, and let's try carbon. Carbon. Well, we know carbon, is what? 2s2p, 2p2, all right? And so we can go, and we know, by the way, that most of the time carbon will hybridize, and so we'll end up with 2 sp3. So n equals 2, sp3 hybridized, all right? So we see that happens. And we also know that carbon's not a metal, and that we have strong bonds, right? In the structure that we're going to talk about, they're covalent bonds, and so they're very strong bonds. So let's do this. Carbon in the gas phase, right? We have 2s and 2p. We know that what happens is we end up with hybridization, and so we end up and we fill these guys. Whoops, not like that. So that's what we get. Now, this would be for diamond in the gas phase. In the gas phase. So with this hybridization, we get bands. All right, we start adding carbon atoms to this, and what do we get? Well, we get a band that's the 2p band, right? The sp3 band is different looking than the bands for magnesium or copper or beryllium, in that there's a separation between the sigma and the sigma star antibonding orbitals, all right? And so we start filling these guys up using Aufbau, and we discover that there's an energy gap, E sub g, between the sigma bonding orbital band and a part of the band and the sigma star band, all right? So what's happening? Well, that's actually pretty good sized. It's about 5.4 electron volts. Now compare that with what? Visible light is around 1 electron volt. Okay, so now we have a very different situation. And there's some terminology we need to have here. This is the so-called conduction band, and this is the so-called, valence band. Conduction band. Valence band and conduction band. So in order for us to get conduction, electrical conductivity, we have to somehow promote an electron across the 5.4 electron volt band gap. This is the so-called band gap, all right? Now we know that visible light is about 1 electron volt, so we know that's not going to do it, all right? And in fact, we might expect that. I mean, a diamond is what? It's transparent to visible light. So if the photons come in, if there's no promotion, there's no emission, transparency to visible light. Okay, so that's a big number. Let's try another one. Let's try silicon. Right? Now I'm going down group 4, okay? Where silicon is going to be also sp3 hybridized, right? So we can do that. Only this time, over here, carbon is what? N equals 2. Carbon is N equals 2. For silicon, N equals 3. N equals 3. And so we can do the same thing. Here's the 3s. Here's the 3p, the 3p, and we hybridize, and we end up with before, and then we end up with a band, same kind of band structure, where this is sigma star, this is E sub g, all right? And this is, again, we'll label it, this is the valence band, conduction band, all right? And now we have states up here. But in this case, what do you figure? N equals 3. So those valence electrons are hanging out further away from the nucleus, right? And we know generally that the energy drops off, the valence electron energy drops off as we get further away from the nucleus. So you might expect that the energy of this gap would be a little bit smaller, and indeed it is. Very fortunate for us. It's 1.1 electron volts. Now we're getting close. Now we're getting close. And so this is 1/4 or even 1/5 of that for carbon. And remember, visible light is on the order of 1 electron volt. So 1.5 electron volts. All right. So what happens? This is close enough, all right, so that we get semiconduction. Semiconduction, and it's called a semiconductor. And we'll make a definition. If the band gap is less than greater than 3 electron volts, we call it an insulator. All right. If the band gap is less than, well, let's give it a range. Let's see. 1 to 3 electron volts, we call it a semiconductor. And of course, if the band gap is equal to 0, we call it a metal. So that's a distinction, which is a little bit arbitrary, but pretty good. So now, if I take a look at silicon, what do I see? Well, if I had a piece of silicon here, as opposed to diamond, and I looked at it, it would be gray. It would have color. And the reason it would have color is because I get some promotion here, and I get re-emission, and so now I get color. So it's not transparent to visible light. All right. Whoops. You know something? I'm going to have to drop down here. All right. Forgot about that. Okay. Let's take a look in general at what we're talking about is photo excitation. All right. Now this is a diagram which is you should have in your aid sheet. Sooner or later, you should have it in your aid sheet. All right. Okay. So let's draw a general band. All right. Right. Here's our two bands. This is the valence band. This is the conduction band, and we have a band gap. All right. We have a band gap. And now what happens if I fire a photon here, right? Well, I guess it depends, right? If E photon greater than E band gap, then what happens? I get promotion of an electron up from the valence band to the conduction band. Okay? So then what happens? Well, the photon is quantized. It's one shot. Photon's gone. Now, I guess we need to settle one little thing. What happens if the photon is really a lot greater than the band gap? In other words, let's say it's 1,000,000 electron volts or something like that. Well, for purposes of 3091, what we're going to assume is that any excess energy goes to heat. Let's not worry about what happens for other things. And in fact, that's not far off. Some of these LEDs that you see, they get warm, all right? So there is some heat, the heat's involved. So the photon, once it goes away, the electron falls back down. Well, if the electron falls back down, then what do I get? I get another photon out, but now I've basically built myself a diode or some kind of device. That photon, the energy of the photon is equal to what? It's equal to the band gap, which is equal to hc over lambda. So I can adjust the wavelength here if I can adjust the band gap. Right? See where we're going. See where we're going with this, right? And well, what happens if I don't know. Let's say I hook this up. I hook this up to a resistor, and I draw current. Well, as long as I keep the light shining on here, the photons, then I can keep promoting these guys, and I can keep drawing current. So what do I have? I have something that I can generate electricity with light, all right? And so that's sort of solar-powered something, isn't it? We can generate current. What happens if I take and now instead of doing that, I hook up a battery to this thing. And now I pump current in here, right? I pump current in here. In that case, I can force the electrons up here, all right? So I can force electrons to go in the reverse, and I can make a photosensor, all right? Or I could force the electrons up here and let them come back down, and I know this wavelength here, I can make a light-emitting diode. So just this one little concept here, right, which is very simplified, gives us the basis for photovoltaics, all right? And that's exactly the way it works. That's exactly the way it works. Okay, let's put this in another way. All right, let's plot the percent absorption. Right? In other words, if the energy's high enough, I absorb. Right? Versus wavelength this way. And since energy is inversely proportional to wavelength, we have energy going this way, all right? And let's put, let's put some numbers in here. Let's say this is 400, and this is 700, and this is Professor Sadoway's dreaded nanometers, all right? So this is visible light. And let's put carbon on there. Well, if you do the calculation, convert it, it turns out that for carbon, with this band gap, you end up with behavior where if the energy is above the band gap, I get 100, well, let's call this 100, that's 0, right? I get 100% absorption. When I get to the band gap, below the band gap, what happens? Well, I drop off, and it goes like that. In the case of carbon, this wavelength, right, which is, by the way, called the absorption edge. The absorption edge, right? That number comes out to be about 229 nanometers. If I try it with silicon, that number, so this would be carbon, this would be silicon, and carbon, if you do that number, What did I do it? Oh, 1125. All right. So the absorption edge, right, for silicon is 1125, which means it absorbs in the visible range. And so that's the way we get luster. And this would be in the what? Infrared. And this would be in the UV region, if you wanted to. Which would be hard UV, and this would be far infrared. Okay, okay, this is the paper, Heitler and London's paper. It's in German, and you can see in Zurich. And this is their original paper. And you can go down to the library and you can get this original paper. And if you know how to read German, we have them. This is some of the original paper. You notice the Schrodinger equation up there. Nasty, really nasty. But this is the calculations. This is radius. This is energy, and you can see a point here where you get an energy minimum, and that's where the bands operate. This is another way to look at it. So this would be the bottom of the bonding orbital and the top of the antibonding orbitals. This is another way to look at what we've drawn so far. Somebody is talking. Something you guys ought to know, this room is acoustically perfect. If you pass gas in the back row, I'll hear it. Okay? So if you're talking up there, I'll hear it. All right? Okay. So you can see what's going on here. We've drawn that. And this is another way to look at it. By the way, there's a mistake in your book. That doesn't make any sense. 2s, 3p. It's 2p in the description for beryllium. Okay, this is another way to look at it. This is in the archival notes. It's one of the few pieces of the archival notes which I don't understand. So don't worry about that. Okay, here's what happens when we illustrated this, where you apply a potential. What happens is you depopulate the bonding orbitals and you populate the antibonding orbitals, and you get conduction. You get conduction. This is the right way to look at it. Okay, this sort of illustrates the things we've gone through the whole time. A metal has no band gap. All right, that no band gap is achieved either by a half-filled set of orbitals or overlap between different levels. An insulator has a large band gap, and a semiconductor has a sort of intermediate band gap. Let's get a little sort of wet your whistle for your reading for next Tuesday. I think we have Monday lecture on Tuesday, right? If you go over to the reactor, they have a reactor here at MIT. Once a week, a truck backs up, and it's full of silicon logs. These things are about 12 inches in diameter, and they're about this tall. And they bring them into the reactor, and they irradiate them with neutrons. Well, what do you think happens? Since everybody in here knows the periodic table by heart, right? Right. What's the next atom? What's the next element over from silicon? Phosphorus. Okay? So guess what? You take and you irradiate the silicon, you absorb a neutron, it adds 1 to Z, doesn't it? And it becomes phosphorus. Well, phosphorus has 1 more electron than silicon. So I have implanted phosphorus into silicon by transmutation. And there's 1 more electron that's in there. Now, where does it come from? I don't know, the electron bank, right? But what do you figure the energy of that guy is? Well, it's a lot higher than the electrons in silicon. All right? A lot higher. And so guess what? That electron, we'll find out, doesn't reside down here. It resides up here, or very close to that. All right? So that's what's called, we'll talk about next time, it's called doping. Only now we're doping it in a special kind of way. Okay, let's keep going. whoops. Let's get this, I want to get this one up there. There we go. Okay, well, shoot. Okay, now, so far we've talked about photons. They're a one-shot deal, all right? What about thermal excitation, all right? Well, we can make the same drawing we have in the past. We got our material here where we have a valence band, conduction band, and now we add thermal energy, all right? By the way, what's the 1 electron volt in temperature? Just to give you a feel. 1 electron volt is 11,600 degrees Kelvin, if you convert that to temperature. So 1 electron volt seems like a small number, but in temperature is pretty warm. Okay, so now the thermal energy is what? It's constant. Unlike the photons, which are one-offs, all right? So it's constant. So what happens? Now I take an electron from the valence band. Here's my gap, and I promote it up here. So it looks sort of like so far up there with photons, but there's one critical difference. It stays up there, all right? It stays up there because the energy is constant, all right? So what does that mean? Well, it leaves behind a broken bond. All right? Leaves behind a broken bond. And that broken bond has a lot of energy. And in fact, it doesn't like to stick around. All right? So given a chance, it'll move. It's like a hot potato. All right? And so that broken bond is called a hole. We're not too imaginative. It's a hole in the lattice, all right? But it has high energy, all right? So what's the deal with this hole? Well, a hole is a zero in a land of -1, all right? So what does it mean? It's actually net positive, net positive. So now, in the case of thermal excitation, I end up with an electron in the conduction band and a hole in the valence band. So I end up with an electron in the conduction band and a hole, and the electrical engineers call this P. They're not very imaginative either, positive, in the valence band. So we get 2 for 1. We get 2 charge carriers for every event, all right? That we get 1. This we get 2 charge carriers for every event. And so now we have what? Let's ask ourselves, can we do a little math on this? And the broken bond, by the way, is a hole, all right? And so the number of electrons is also equal to the number of holes, all right? Because it's a 1 for 1, and in the electrical engineering world, they say N equals P, all right? N equals P, all right? And so we can now go back and say something about this conductivity. We can do some calculations here, and we can calculate the conductivity due to the electrical conductivity, and it's really the sum over I of N of I, which would be the number of the population of carriers. Right? times the absolute value of the charge on the carrier times something called the mobility. The mobility. Okay, so what's the mobility? Well, you can imagine that these electrons have to move back and forth in the lattice, and in a metal versus a covalent solid or something like that, it might be a little bit different. The resistance might be different, and so in fact it is. Mu I is equal to the velocity of the charge carrier divided by the electric field. The electric field. Okay, so we're almost there. We're almost there. Now we need to, and we can simplify this because of the n equals p business, and we can say that the electrical conductivity is equal to what? It's equal to n sub e times E, which is the electronic charge, times mu sub E, all right, plus n sub H, which would be the holes, electronic charge times mu sub H. But since n is equal to P, we end up with n sub E times the electronic charge times mu sub E plus mu sub H. All right? Okay. And so that what we really need to get is this. Well, we don't have time to go through that, but from a quantum mechanical calculation, we can get that. N sub E is equal to what? It's equal to some constant times t to the 3/2 times the exponent of minus E sub g over what? Over 2k sub b times t. So what is all this stuff? Well, this is a constant. This is the temperature. Makes sense. This is the band gap. So it's a representation of the binding, right? It represents binding. And what's down here? Well, K sub b is Boltzmann's constant. This is absolute temperature. And so this represents the disruptive force. Well, disruptive, just call it disruptive, right? So it's a balance between how tightly they're bound and how much energy I've got to do this. Well, let's, we've got 1 minute, okay? Let's do a quick calculation for silicon. Let's, just to close the loop here. For silicon at room temperature. At room temperature, that number comes out 1.3 times 10 to the 10th per centimeter cube. Say, well, you know, that's billions. That's a big deal. Well, what about copper at room temperature? Well, that number comes out about 8.5 times 10 to the 22. Now we're talking big numbers, all right? So there's a 10 to the 12th difference between these two. Well, let's take a quick look before we finish up. Okay, this is the band gap as a function of position in the periodic table. Now, you guys ought to be able to rationalize this, right? Lead is a metal. Bigger atoms, you can see. Tin actually comes in two flavors, gray and white, and one of them, I think it's white, actually forms covalent bonds. And they use tin for night vision. Think about where that band gap is, right? But here's the punchline. We were trying to rationalize this large difference in conductivity. Well, there's copper up there at 10 to the 7th. There's silicon at 10 to the minus 4. And 10 to the minus 4, 10 to the minus, it's about 10 to the 12th or thereabouts. And so, lo and behold, this we were able to rationalize with these fairly simple models the range of conductivities that go all the way from metals to semiconductors and even diamond. Look at diamond, 10 to the minus 11th, right? You can rationalize that. The band gap, where's the band gap? 5.4 electron volts. Okay, we're out of time.